Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin. A peculiar and bitter victory marked the year 1734. The Paris Academy of Sciences, the epicenter of European intellectual life, announced the winner of its prestigious grand prize. The topic concerned the inclinations of planetary orbits, a deep question of celestial mechanics. The Academy, however, found itself unable to choose between two submissions of extraordinary merit. It declared a tie, splitting the prize between Daniel Bernoulli and his own father, Johann. For Daniel, this should have been the pinnacle of recognition, a moment of shared glory with the patriarch of Europe's most formidable scientific dynasty. Instead, it was a catastrophe. Johann Bernoulli, a man of ferocious ego and volcanic temper, perceived this sharing of honors with his son as an unbearable insult. He threw Daniel out of his house, and the two would remain estranged for the rest of their lives, a schism born from a triumph. This moment reveals the crucible in which Daniel Bernoulli was forged, an environment of staggering intellectual brilliance perpetually superheated by familial rivalry. His life's work would become an act of profound intellectual independence, a declaration that his genius required its own orbit. The Bernoulli family of Basel, Switzerland, was less a lineage and more a mathematical singularity. Daniel's uncle, Jacob, had pioneered the calculus of variations and established the law of large numbers. His father, Johann, was a titan of analysis, a collaborator and fierce rival of Leibniz and Newton, who tutored the great Leonhard Euler. To be a Bernoulli was to inherit a legacy of genius and an expectation of greatness, coupled with a propensity for acrimonious public disputes over priority. Johann, recognizing his son's prodigious mathematical gifts, attempted to steer him toward a more practical and lucrative career in business or medicine, perhaps fearing the emergence of yet another rival under his own roof. Daniel acquiesced to his father's command to study medicine, but his mind refused to be compartmentalized. His 1721 doctoral dissertation on the mechanics of respiration was a masterpiece of iatromathematics, a field seeking to explain physiological processes through mechanical laws. He modeled the action of the lungs and diaphragm using principles of physics, a clear signal that his intellect would always seek the universal language of mathematics to describe the world, whether the subject was a planet or a human organ. His true intellectual apprenticeship began in 1725, when he and his brother Nicholas were invited to the newly established Imperial Academy of Sciences in St. Petersburg. There, in the company of his friend and former pupil of his father, the incomparable Euler, Daniel found the freedom to pursue his deepest interests. The intellectual atmosphere was electric, a stark contrast to the stifling environment of his father's home. It was in Russia that the seeds of his most famous work, Hydrodynamica, were sown. The book, finally published in 1738 after his return to Basel, represented a monumental leap in the understanding of matter in motion. The central problem confronting 18th-century physics was the behavior of fluids. Newtonian mechanics had provided a breathtakingly successful framework for understanding the universe on a grand scale, treating planets and projectiles as discrete point masses moving through a void. The principles of force, mass, and acceleration worked beautifully for solid objects. A fluid, however, was a different kind of entity. A river, a gust of wind, or the blood flowing through an artery represented a continuous medium, a substance whose internal parts moved relative to one another in complex ways. The challenge was to find a unifying principle, a single mathematical law that could describe the intricate dance of pressure, velocity, and energy within a moving fluid. While engineers had developed empirical rules for managing water, and philosophers had speculated about its nature, a coherent mathematical physics of fluids was absent. Daniel Bernoulli's solution was an act of profound physical intuition and mathematical elegance. He approached the problem by returning to a principle championed by Leibniz in his debates with the Newtonians, the conservation of vis viva, or living force. Today we recognize this as a precursor to the law of conservation of energy. Bernoulli imagined a fluid as a collection of infinitesimally small particles, each possessing its own energy. By applying the conservation of vis viva to the entire system of the fluid, as it moved through a pipe or channel, he derived a single powerful equation. This formulation, which we now call Bernoulli's principle, established a fundamental relationship. It states that for an idealized incompressible fluid in steady flow, the sum of three quantities remains constant along a streamline. These quantities are the pressure within the fluid, the kinetic energy per unit volume, which is expressed as 1/2 times the density ρ times the velocity v squared, and the potential energy per unit volume, expressed as the density ρ times the gravitational acceleration g times the height h. The equation P plus 1/2 ρ v squared plus ρ g, h equals a constant, was a revelation. It was a statement of energy conservation tailored specifically for the dynamics of fluids. The implications were immediate and far-reaching. The principle explained, with mathematical certainty, a phenomenon that was observable yet poorly understood. Where the velocity of a fluid increases, its internal pressure must decrease. Consider water flowing through a pipe that narrows into a constriction. To maintain a constant flow rate, the water must accelerate as it enters the narrower section. Bernoulli's equation dictates that this increase in kinetic energy must be paid for by a corresponding decrease in the fluid's pressure. This inverse relationship between speed and pressure was the key that unlocked a host of physical mysteries. It was a conceptual tool of immense power, reducing complex behaviors to a single, elegant trade-off within an energy budget. The enduring legacy of this principle is woven into the fabric of our modern technological world. It is the fundamental concept that explains aerodynamic lift. The curved upper surface of an aeroplane's wing forces the air flowing over it to travel a longer path, and therefore a faster one, than the air flowing along the flat bottom surface. According to Bernoulli's principle, this higher velocity on top creates a region of lower pressure, while the slower moving air below exerts a higher pressure. The resulting pressure differential creates an upward force, lifting the massive aircraft into the sky. The same principle governs the function of a carburetor, where air rushing through a narrow throat, called a venturi, creates a low-pressure zone that draws fuel into the airstream. It explains the operation of atomizers, paint sprayers, and even the dangerous pull one feels when standing too close to a speeding train. With the publication of Hydrodynamica, Daniel Bernoulli had established a new branch of physics. He had provided the mathematical foundation for understanding a state of matter that permeates our planet and our bodies. Yet this triumph was forever tainted by his father's reaction. Upon seeing his son's work, Johann rushed to publish his own treatise on the subject, which he titled Hydraulica. In an act of shocking academic dishonesty, he deliberately backdated its publication year to 1732, attempting to steal priority for the discoveries his son had pioneered. This final betrayal severed their relationship permanently. Daniel had won the intellectual argument, but the personal cost was immense. His work on fluids had laid down a law for the predictable mechanical world. Having charted the currents of water and air, his restless intellect began to drift toward a domain governed by far more elusive forces, the realm of human judgment, fortune, and risk. The intellectual landscape of the early 18th century viewed probability as a tool for gentlemen gamblers and actuaries, a precise calculus for the objective world of dice rolls, card draws, and life annuities. This was the domain of Pascal, Fermat and Huygens, a mathematics that could calculate the fair price of a lottery ticket or the odds of drawing a royal flush. Its logic was impeccable, its calculations elegant, yet a profound disconnect existed between this pristine mathematical expectation and the messy, often perplexing reality of human behavior. A particular thought experiment, born from discussions between Daniel's cousin Nicolas Bernoulli and the French mathematician Pierre-Raymond de Montmort, brought this intellectual crisis to a head. It became known as the St. Petersburg paradox, and its resolution would require a fundamental rethinking of the very meaning of value. The paradox presents a deceptively simple game of chance. Imagine a casino offering a game where a fair coin is tossed repeatedly until it lands on heads. If heads appears on the first toss, the player receives 2 ducats. If it appears on the second toss, the payout is 4 ducats. If on the third, 8 ducats. And so on, with the prize doubling for each additional toss required. The question is straightforward. What is a fair price to pay to enter this game? The classical theory of probability offered a clear method for calculation. One computes the expected monetary value by summing the potential payouts, each weighted by its probability. The probability of getting heads on the first toss is 1/2, for a payout of 2 ducats, contributing 1 ducat to the expected value. The probability of the first heads appearing on the second toss is 1/4, for a payout of 4 ducats, contributing another ducat. On the third toss, the probability is 1/8 for a payout of 8, again adding 1 ducat. The sum becomes 1 + 1 + 1, continuing indefinitely. The expected monetary value of this game is therefore infinite. According to the prevailing logic, a rational person should be willing to risk their entire fortune to play. Yet, as Daniel Bernoulli observed with his characteristic insight into human nature, any reasonably prudent individual would find such a proposition absurd. Most people would hesitate to pay even 20 ducats for a single chance. This glaring discrepancy was a deep intellectual wound. It suggested that the mathematical framework for rational decision-making was either incomplete or profoundly misguided. The problem lay in the assumption that a ducat holds the same value for everyone at all times. In his 1738 paper, published in the Commentaries of the Imperial Academy of Science in St. Petersburg, and titled Specimen Theoriae Novae de Mensura Sortis, or Exposition of a New Theory on the Measurement of Risk, Daniel Bernoulli offered a solution of breathtaking originality. He proposed a radical reorientation of the problem. He argued that the true measure of a choice's worth is its psychological value, its utility to the individual. The gain of 1,000 ducats to a pauper who possesses nothing is a life-altering event. The same 1,000 ducats to a millionaire is a trivial addition. The monetary amount is identical, but its utility, its capacity to produce satisfaction and well-being, is vastly different. This concept, today known as the principle of diminishing marginal utility, posits that the utility derived from an additional unit of wealth decreases as one's total wealth increases. Bernoulli then gave this psychological insight a rigorous mathematical form. He proposed that the utility gained from an increase in wealth is inversely proportional to the amount of wealth already possessed. Using the language of calculus, this relationship can be expressed by stating that the differential of utility, du, is proportional to the differential of wealth, dx, divided by the amount of wealth, x. Integrating this expression yields a powerful result. The utility of wealth is a logarithmic function of the amount of wealth. Utility, he proposed, is proportional to the logarithm of x. This formulation beautifully captures the intuition. As wealth, x, grows larger, its logarithm grows ever more slowly. The exponential increase in monetary payouts in the St. Petersburg game translates into a mere linear or arithmetic increase in psychological satisfaction. Armed with this new tool, Bernoulli returned to the paradox. A player should evaluate the game based on its expected utility, their expected psychological gain, which is a far more personal and realistic calculation. The expected utility is the sum of the utilities of each possible outcome, weighted by their probabilities. For a person with some initial wealth, the calculation yields a finite, and typically quite small, value. This finite expected utility corresponds to a certain monetary amount, the certainty equivalent, that a person would be willing to pay. This amount is modest and aligns perfectly with observed human behavior. The paradox dissolved. Bernoulli had successfully integrated a subjective psychological principle into the objective mathematical framework of probability. He had shown that a person's decision is governed by their internal evaluation of gain relative to their current state, a profound departure from the idea of a universal absolute monetary value. The implications of this work extended far beyond a clever resolution to a vexing puzzle. Bernoulli had laid the cornerstone for what would become modern microeconomic theory, game theory, and behavioral finance. The concept of utility maximization is now the fundamental axiom describing rational choice in economics. It provides the mathematical language to understand and quantify risk aversion, explaining why people purchase insurance. They are willing to pay a small certain premium to avoid the possibility of a large catastrophic loss, thereby trading a lower expected monetary value for a higher expected utility. It underpins the entire theory of portfolio management, which advises diversifying investments to balance risk and reward. 2 centuries later, John von Neumann and Oskar Morgenstern would build upon Bernoulli's foundation to develop their axiomatic utility theory, a pillar of 20th century social science. By looking at a simple coin toss game and asking a deeper question about human desire, Daniel Bernoulli had opened up a new continent of thought. He had demonstrated that mathematics could illuminate the inner world of human judgment with the same power it brought to the outer world of celestial mechanics and fluid dynamics. Having quantified the subjective realm of human choice, Bernoulli would soon turn his attention back to the physical world, seeking to uncover the hidden mathematical harmonies within the phenomena of sound and vibration. Having plumbed the depths of human decision-making, Daniel Bernoulli returned his gaze to the tangible world of mechanics, where a different kind of harmony awaited discovery. The intellectual landscape of the mid-18th century was dominated by a challenge of profound elegance and difficulty, the problem of the vibrating string. This was the crucible of mathematical physics, a question that drew in the era's most formidable minds, including Leonhard Euler and Jean-Laurent D'Alembert. The problem appeared simple: describe mathematically the motion of a taut string, like that of a violin or harpsichord, after it is plucked or struck. Yet, this simple physical system concealed deep questions about the very nature of functions, continuity, and the capacity of a single equation to govern an infinity of possible behaviors. The groundwork had been laid with magnificent clarity. D'Alembert, in a landmark 1746 paper, had derived the governing partial differential equation, a beautiful expression now known as the one-dimensional wave equation. It states that the acceleration of any point on the string is proportional to its curvature. Mathematically, the second partial derivative of the string's displacement with respect to time equals a constant, the square of the wave speed, multiplied by the second partial derivative of its displacement with respect to position. D'Alembert presented a wonderfully general solution, expressing the string's shape as the sum of two traveling waves moving in opposite directions. Euler refined and expanded upon this, yet a fierce debate ensued. The core of the controversy revolved around the initial condition. A string can be plucked into a sharp, angular shape. How could such a form, with a distinct corner, be described by a smooth, well-behaved analytical expression, the only kind of entity that 18th-century mathematicians were comfortable calling a function? The debate was a philosophical impasse, a collision between the messy reality of physical phenomena and the pristine, idealized world of analytic formulas. Into this highly formalistic debate, Daniel Bernoulli interjected a piece of profound physical intuition, an idea born from the acoustics of the music he so loved. He approached the problem from an entirely different conceptual framework. Where his contemporaries saw a single complex curve evolving in time, Bernoulli heard a composite sound. He recognized that any musical tone produced by a string is a blend of a fundamental frequency and a series of higher, integer multiple frequencies, the overtones or harmonics. This physical reality, he reasoned, must have a direct mathematical counterpart. He proposed that any possible motion of the vibrating string, regardless of its initial complexity, could be represented as an infinite sum, a superposition of its elementary modes of vibration. Each of these modes was a simple, elegant standing wave described by a sine function. His solution was a radical departure. He asserted that the displacement of the string, which we can call Vol I as a function of position x along the string and time, could be written as a series. This series is the summation, from n equals 1 to infinity, of terms, each consisting of a coefficient, let's call it a sub n, multiplied by the sine of n times pi times x, divided by the string's length L, which is then multiplied by the cosine of n times pi, times the wave speed c times t, all divided by L. This formulation was a complete physical model captured in a single expression. Each term in the sum represents a pure harmonic. The n equals 1 term is the fundamental tone, a single graceful arc vibrating up and down. The n equals 2 term is the first overtone, vibrating in two segments with a stationary point, or node at its center. The n equals 3 term has 3 segments and 2 nodes, and so on for all integers n to infinity. The coefficients, the a sub n terms, determine the amplitude or loudness of each harmonic in the total sound. Plucking the string at its center would excite primarily the fundamental mode. Plucking it elsewhere would introduce a richer mixture of these higher harmonics. This brilliant insight, which perfectly married physics and mathematics, was met with considerable skepticism, most notably from his close friend Euler. For Euler, the proposal was aesthetically compelling, but mathematically problematic. How could an infinite sum of perfectly smooth, endlessly differentiable sine functions ever add up to produce the sharp corner of a plucked string? The prevailing mathematical understanding suggested this was an impossibility. The sum of analytic functions, it was believed, must itself be an analytic function. Bernoulli's proposal required a leap of faith, an acceptance that an infinite series could possess properties that its individual terms lacked. The disagreement between Bernoulli and Euler was a classic and deeply illuminating scientific dispute, pitting a powerful physical intuition against the rigorous, established canons of mathematical analysis. History, of course, would vindicate Bernoulli's physical vision. The mathematical tools to furnish a rigorous proof were yet to be developed, but the seed he planted was revolutionary. It would take another half-century for the full flowering of his idea. Working on a completely different physical problem, the conduction of heat in solid bodies, the French mathematician Joseph Fourier would develop the formal apparatus to prove that an astonishingly broad class of functions, including those with corners and discontinuities, could indeed be represented by an infinite series of sines and cosines. This technique, now known as Fourier analysis, provided the solid mathematical bedrock for Bernoulli's principle of superposition. It confirmed that the infinite sum of smooth waves could indeed converge to a non-smooth shape, validating the physical insight Bernoulli had championed against the titans of mathematics. The consequences of this concept are difficult to overstate. The idea that complex waveforms can be decomposed into and synthesized from simple sinusoidal components is a cornerstone of modern science and technology. It is the fundamental principle behind all digital signal processing. The compression algorithms that allow for the storage and transmission of digital music in formats like MP3 and images like JPEG work by breaking down the complex sound or light wave into its constituent frequencies and discarding the ones our senses are least likely to perceive. In quantum mechanics, a particle's wave function is understood as a superposition of its possible energy states, a direct intellectual descendant of Bernoulli's vibrating string. In acoustics, architecture, and structural engineering, analyzing the response of buildings to vibrations from earthquakes or wind relies on decomposing complex forces into their fundamental frequencies. Bernoulli's work on the vibrating string thus represents far more than the solution to a fashionable 18th-century puzzle. It reveals his characteristic genius for identifying a deep, unifying physical principle and giving it a powerful, predictive mathematical form. He possessed the confidence to let physical reality guide his mathematics, even when it led him beyond the accepted boundaries of contemporary formalism. This ability to synthesize ideas from disparate domains, to see the harmonic series of a violin string as a key to a universal mathematical truth, would continue to define his work as he applied the rigorous principles of mechanics to new and even more complex systems, including the very structure of living organisms. This intellectual impulse found one of its most audacious expressions in his attempts to quantify the mechanics of life itself. In an era when physiology was a descriptive science, rich in observation yet poor in mathematical rigor, Bernoulli sought to apply the cold, precise laws of hydrodynamics to the warm, pulsing flow of blood. His work in this area, sometimes called iatrophysics, represented a profound conceptual shift. He treated the body as a physical system, an intricate machine whose operations could be understood through the language of pressure, velocity, and work. Within his masterwork, Hydrodynamica, he dedicated a section to this very topic, a treatise in its own right, titled Hyomostatica. Here Bernoulli modeled the heart as a mechanical pump and the arterial network as a system of elastic pipes. He endeavored to calculate the work performed by the heart with each contraction, a calculation that required estimating blood pressure and the volume of blood ejected. He effectively sought to measure the horsepower of the human heart, an organ more commonly associated with poetry than with pistons. He applied his own fluid principles to analyze how pressure would change as blood flowed from wider arteries into narrower capillaries, recognizing the interplay between velocity and pressure within the circulatory system. This pioneering effort to create a quantitative mechanical model of blood flow laid a crucial foundation for the entire field of modern hemodynamics. While today's models are vastly more sophisticated, accounting for the non-Newtonian properties of blood and the complex, branching geometry of the vascular tree, the essential premise remains Bernoulli's, that the laws of physics are as valid inside the human body as they are outside of it. His analytical gaze extended from the flexible tissues of the body to the rigid materials of human construction. The 18th century witnessed increasingly ambitious architectural and engineering projects, which created an urgent practical demand for a deeper understanding of the strength of materials. The question of how a horizontal beam sags under its own weight, or an applied load was a puzzle that had intrigued thinkers since Galileo, yet a comprehensive mathematical theory was elusive. Working in a period of intense intellectual exchange and competition with Leonhard Euler, Bernoulli co-developed the foundational theory of beam elasticity. This work, now known as the Euler-Bernoulli beam theory, remains a pillar of civil and mechanical engineering. Bernoulli's key insight was to formulate a relationship between the external forces acting on a beam and its internal geometric response. He proposed that the internal bending moment at any cross-section of the beam is directly proportional to the curvature of the beam at that point. This is captured in the elegant differential equation m equals E times I times kappa, where m is the bending moment, kappa is the local curvature, and the constant of proportionality is the product of E, the Young's modulus representing the material's stiffness, and I, the second moment of area describing the cross-section's shape and its resistance to bending. This equation was revolutionary. It transformed the problem of beam deflection from an empirical guessing game into a solvable problem of calculus. By integrating this equation, engineers could predict the exact shape a beam would take under a given load, allowing for the design of structures that were both safe and efficient. The bridges we cross and the buildings we inhabit are silent testaments to the predictive power of this formulation. To contemplate the full arc of Daniel Bernoulli's career is to witness a mind of extraordinary scope and unifying vision. His contributions span fluid dynamics, probability, statistics, acoustics, physiology, and structural mechanics. A lesser intellect might have produced a collection of disparate achievements, a series of isolated solutions to isolated problems. Bernoulli's body of work, however, reveals a deep coherence, a persistent application of a few powerful, overarching principles to a vast range of phenomena. The principle of the conservation of energy, what his era called vis viva, animates his analysis of flowing water. The principle of superposition, the idea that complex vibrations are sums of simpler ones, provides the key to the vibrating string. The search for an optimal path, a mathematical minimum or maximum, informs the thinking behind his economic and probabilistic reasoning. His legacy is this demonstration of the immense power of mathematical physics to serve as a universal language. He saw the same fundamental truths operating in the rush of a river, the thrum of a violin, the branching of an artery, and the calculus of human choice. His life also serves as a profound and intensely human story about the nature of scientific progress. It was a life defined by collaboration and by conflict, by the brilliant synergy with his friend and peer, Leonhard Euler, and by the painful, destructive rivalry with his own father, Johann. This dynamic of ambition, competition, and shared discovery fueled the incredible intellectual output of the era. Daniel Bernoulli's ultimate triumph was his ability to look at the complex, messy world and perceive the simple, elegant mathematical structures that govern it. He left behind equations and principles that are now fundamental tools of science and engineering, and something more, a powerful testament to the idea that a single coherent intellectual framework can illuminate the deepest workings of the universe.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.